Good morning and welcome to another episode of Talk on the Rocks. Uh, it is August 10th. This is the third time I've had to record this. I have been riddled with problems. I have not recorded since January. I've been working for the last 3 or 4 months on this Hawaiian lecture of Hawaiian volcanism from birth to extinction. I tried recording twice only to find out the videos were unwatchable due to jittery lunges and just the camera recording myself was just terrible, and everything was just jumpy. I don't know what it was. I had to reset my video formats and all this stuff. So in any case, it's been very challenging to sit and blab for about an hour and a half only to find out that everything you've said cannot be used and has to be deleted. So in any case, I hope that this one works. I hope that this one goes through. This is a, a very challenging lecture for me, especially the beginning because it's riddled with geochemistry. And if I don't do the geochemistry, I cannot back up my arguments. And you know, maybe recording these twice already has allowed me to iron out some of the wrinkles because the geochemistry is extremely confusing, even for me. I work myself into corners that I cannot get myself out of, which means I have to disrupt the flow. In any case, I'm going to try to simplify that. So anyways, this is Talk on the Rocks, Evolution of a Hawaiian Volcano, Life Stages of Hawaiian Volcanoes from Birth to Extinction. I can say for sure that this is a very special lecture for me. When I left home, Hawaii 14 years ago to come home here, and a little bit of information, I spent the majority of my adult life in Hawaii. 23 years to be exact. I was educated there. I went to the University of Hawaii in Manoa. I met a excellent and amazing, just wonderful group of friends over there that I miss terribly. So shout out to those guys should you be watching this. And I will be returning in late March, early April. What was interesting though for me is that when I came home here, I wanted to do a lecture on the, where I'm from, and I ended up doing one, the entire Earth history and into 250 million years of New England geology. And the work I did there to learn, all the island arcs and the accretion, basically the whole history of the North American continent, really helped me with some of this, especially because that had a lot of geochemistry. And it's interesting that the work I did there helped me do and finish my work doing, working on, New England geology. But then I was also able to take the tools and go back there and, and work on something that's from there and utilize the geochemistry I learned from here. But of course, the geochemistry, when I started doing Hawaiian volcanism, just went off the charts and I went into the rabbit hole very deep. But it has been an amazing learning process. So in any case, with no further ado, we shall go and learn about Hawaiian volcanism. This picture here is from Mauna Kea. This is one of the post-shield cinder cones, one of the more symmetrical ones to be exact. People will hike this and ski down. In the background is Mauna Loa. Of course, as you can see, Mauna Loa is very domed, whereas Mauna Kea is very, very hummocky. And there are all sorts of reasons for that, what I'll go into later. So an overview of this lecture. What we're going to do is we're going to take a quick look at the current Hawaiian archipelago, ages, stages of island formation, hotspot movement, cross-section of oceanic crust under the islands. This is basically just giving a 101 review of what we, most of us already know. If you're watching this and you don't know any of this stuff, it's the rest of the lecture I'm going to tell you right now will not be easy. However, you make it through this first chapter, or this first lecture. I think I'm going to break this into 3 or 4 parts. You will be very rewarded because you'll understand a lot more why the volcanoes behave the way they do. Next up, we'll do the Hawaiian plume, and that involves mega plumes or super plumes within the Earth. There's 2 of them to be exact. They have a tendency to hang out sort of near the equator, one under Africa, one under the Southwest Pacific Ocean. They are named Tuzo and Jason. They have a lot of research has gone into these in the last 30 years or so, so much so that we pretty sure that they remain stationary. They end up these huge mega plumes are right off the outer core of the Earth. They are just gigantic, and they really are the guys calling the shots for the rest of the planet. When these things decide to get agitated and pop out something on the surface of the planet, it can generally lead to things like extinction events, continental breakups, all sorts of crazy things. These are, we think, the generational areas of our LIPS, large igneous provinces, that absolutely decimate the planet periodically throughout life. I think, 3 of the 5 major extinctions involve LIPS, large igneous provinces, and they are most likely tied to the peripheries of these megaplumes. Is in regards to Hawaii coming back home, the megaplume Jason, on the northeast side of it, is the location of the Hawaii plume. And we think that these plumes, the boundaries, it's kind of like a storm in the summer. You have one side that's unstable and has all sorts of junk in it. The other side is real stable and doesn't have a lot of junk in it. And when these two mix, you have uplift and mixing and all sorts of reactions, and you generate a plume that feeds the Hawaiian volcanoes. And within the Hawaiian plume, there are 2 trends, the Loa and Kea trend, and they basically define the type of volcanoes or the magmas that comes out of each volcano. And I'll go into that in much more detail in a little bit. We'll go over the geochemistry of the magmas. We'll learn about niobium and lead. These are 2 big things that dictate whether something has been around for a long time, the source of it. Basically, we look at these things to see where the origin of the magmas that are upwelling in the plume of the Hawaiian hotspot through the use of lead and niobium, and I will go into that in great detail. We'll also look at cross sections, the melting zones, the conduits, and other such things that are beneath the Hawaiian volcanoes, the upper magma chambers, lower magma chambers, conduits, and plume generation areas, magma generations, etc. Then we will look at stages of Hawaiian volcanoes. This will probably be in part 2. We have the pre-shield, the shield, post-shield, the first erosional rejuvenation, extinction, erosion, submersion, accretion. Pre-shield is where Loihi is. Shield building is, I don't know why I sway like that. I just do when I start doing this part. Shield building is Mauna Loa and Kilauea. Post-shield is Hualalai, Mauna Kea, possibly Kahala. Kahala may be entering the first erosional stage. Haleakala, and then after that, things are further. They're either in erosional or rejuvenation stage. The first erosional stage might be someplace like Kohala. I don't want to use West Maui because it has rejuvenated 4 areas of rejuvenated volcanism. Possibly Lanai. However, Lanai seems to have bypassed the post-erosional stage for reasons I will go into later. Then, of course, the rejuvenation stage is all the way from West Maui, Molokai, Oahu, Kauai, Niihau, etc. We see evidence of post-erosion, of rejuvenation eruption on those. And of course, extinction, erosion, submersion, and accretion is when the volcano finally dies. You become a seamount, you erode, and then the seamount actually begins to sink, and then you eventually accrete somewhere up near the Aleutian Islands or Kamchatka, or you may just sink as the downgoing slab goes and extends right before the actual plunge, and you may just sink and just get sucked out. We're not sure. After that, I will go over each of the main Hawaiian islands, Hawaii, Maui, Koholalave, Lanai, Molokai, Oahu, Kauai, Niihau, and the northwestern Hawaiian Islands. I will go over the volcanoes, the history of them, odd pieces of trivia, things that make them unique, the eruption cycles, what have you. And then at the very end, then this is still a work in progress here. I will do select examples of evolutionary stages. So we'll do the Luihi, Kilauea, Hulalai, Mauna Kea, Kahala, Haleakala, Lanai, Molokai, West Maui, Ko'olau, Waianae, and Kauai. And each one of these, you've got your shields, you got your post shields, you got, early post shields, mid post shields, late post shields. Then you have, Lanai, Molokai, where you have all sorts of things going on, sort of like the Big Island, but, one evolutionary step further ahead. And we're going to discuss why there's some have shields, some post shields, some do not. Some may be in rejuvenation, dormancy, and some just may be extinct. West Maui, this is very intriguing what's going on over there. We have some small areas of rejuvenation, but it may be extinct. But I have a hard time believing that would be the last gas. Akolau and Waianae, a good study area for a Kea and a Loa. Not a Kea and Loa, I'm sorry. For two volcanoes on the same island that are inherently very different. And then, of course, Kauai, our oldest island, which has everything going on. It's like a huge package. So when I see Kauai with all the, the late rejuvenation stage magmatic activity, hard for me to believe that Oahu's done. Especially since it's actually erupted in a shorter period of time. I think Kauai's 150,000 since the last one, but Oahu may be as little as 40,000. So anyway, work to be done on that. So the Hawaiian archipelago, as you can see, you have your Hawaiian chain here, you have the Emperor Seamounts here, and of course you have a huge bend here. Again, I've gone over this a few times, and I'm just going to stick to the same scenario that I don't really know what happened here. I can only speculate. There's a few ideas kicking around, well, if I was to make a guess at it, and I think I'm ready to start making guesses, I'm at that point. When the plate was going this way, you really had subduction going under here and probably here. And then all of a sudden it kind of goes this way. Well, my theory is maybe that this began to unzip over here. So in other words, this is now, slab pull down over here is much larger than it is up here. And so maybe just by, the path of least resistance, as this began to unzip down, movement started going this way. But it's weird because you would think it would be, it's really abrupt. If this unzipped, this is this is thousands and thousands of miles, you'd think it would be somewhat abrupt. Somewhat, what's the word I'm looking for? It'd be somewhat slow to occur. In other words, it'd be gradual. It doesn't look that way. It kind of goes boom right here. So, if it really unzipped quickly, yes, that could, that could explain this. It could be something to do with Jason under here, the massive super-plume. Could be, it could be a lot of things. But in any case, something shifted here. You have a couple of pieces of these look like hotspot plateaus somewhere. You also have a transform fault zone that kind of goes right through here. All of these could play a little bit about what's going on. I don't know if maybe this eruption, I don't know if this even is an eruption. It certainly looks like there's some sort of flood basalt here. And this down here, I'm going to make a guess that this is much younger than this because there's nothing sticking up yet. In other words, the arcs have not had a chance to build up, islands, big ones anyways, more like here and here and here. So this kind of tells me, I'm not 100%, I'm just guessing and speculating that this may be younger. And what's happening is as this plate falls, it is just pulling everything this way. And I think the eventual demise of the Pacific is this thing just continually gets pulled this way and stretching out this area over here, maybe creating a new ocean, a back area here. I don't know. But something very, very conspicuous happened here. All seamounts and the Emperor seamounts are underwater. They progressively get lower, and then they eventually. And this is an interesting thing. It seems to go right here. Is this a coincidence that they sort of end up in this little notch? I don't know. The chances of the oldest Hawaiian Emperor seamount going in under here right at this particular time would be very rare. and almost it'd be an astronomical coincidence. So why don't we see them here? We do see a bulge, but what I think happens is we know that underneath when you have a steep subduction zone, and I believe this is fairly steep, you have stretching right here before you plunge, and maybe that's enough to thin the crust and have these sink, and that's why you have sort of this blob area here. I don't know. It's just a possibility. Anyways, you start seeing the islands around in here, and of course they get progressively younger to the south and east, and older to the north and west. Emperors get older straight north, and younger straight south. All right, map of the main Hawaiian Islands. This is something that if you're watching this again, I'm really would hope you're familiar with. You have the Ni'ihau Kauai system here, Oahu, Molokai, Lanai, Ko'olawe, Maui, and of course the Big Island. And of the volcanoes, you have the Ni'ihau volcano, you have the massive Kauai, you have Kaina over here, you have Waianae, you have Ko'olau right here, you have some huge slides. You have the Penguin Bank, which is most likely an extension of the West Maui, West Molokai. I'm not 100%. I think we consider it, I'm not sure. Lanai right here, Maui, I'm sorry, Haleakala, and the West Maui and Ko'olawe. And if you were to, it doesn't take a lot of imagination to realize that this is pretty much the outline of Maui Nui, which was, basically about half the size of the Big Island in its heyday. I think that's an underestimation. But you can see the old shorelines right here. You can see some old shorelines here from where Kahala and Mauna Kea have been sinking, but yet there are none here because these mountains are so new and they have not sunk sufficiently yet. Between here and here, and I would say that this area right here is the most dangerous part in Hawaii, with the exception of the unstable coast of the south shores of the Big Island. As the Big Island grows, it is literally flexing up Oahu. It has been for a while. It's flexing up this area here, and the whole thing is tilting this way. And so you're getting the weight of Haleakala slowly, basically the weight is shifting and forcing itself into an area where there's nothing supporting it. And you can see a couple, like this is a Ko'olawe slump, you can see that chunk came out right there. And you can see what looks like maybe a slump here. This is going to collapse. And when it does, it's going to open up this mountain, and it's absolutely going to decimate this coastline here, and probably all over, and of course here. I would just basically not be around. I would recommend not being around when that occurs, because this is going to be a catastrophic landslide. And they've happened before. You can see the marks out here. This is a landslide here, and that's a landslide there. And these things go out, 100 miles. Not 100, but yeah, about 100 miles. And some of these chunks are the size of Manhattan. So what wave that produced, don't know. But how you get something to travel that far away is fairly, it's shocking. And there's slides everywhere. So this is not unusual. I mean, so the islands have, this is a slump from the Waianae Mountains. You've got slumps over here from Kauai. They're all over the place. This is an age, a map of the age, rough age of the Hawaiian Islands. Not to take anything away from Ken Han. These are just sort of average superficial ages. These do not represent the true age of the volcanoes because, let's face it, getting an age from the base of any of these mountains, unless you've drilled down, is not easy to do. So, for instance, Oahu's probably been going active for about 400,000. I mean, for about between 200,000 and 400,000 years. It's 50,000 feet below the surface. It's 3,000 feet below the surface. We expect another 50,000 years it will break. Kilauea has probably been going on for 400,000 maybe, 500,000. Mauna Loa, probably about 1 million. Mauna Kea, a little bit more. Hualalai, about 800,000. Hualalai is a weird one. It's the flux is so much smaller that it's hard to imagine that a volcano of this size would be so much older than one of this size, but it seems to be that. So I always put question marks of the age of Hualalai. Kohala about 1.1, 1.2, 1.6 maybe here on Maui. So you have to add ages as you go deeper, obviously. Now, Kauai definitely has lavas that are younger than Ni'ihau, but as a whole, I believe Ni'ihau is younger. Is older than Kauai, so maybe these need to be reversed. I don't know. It might have just been a typo. But in any case, general trend, southeast younger, northwest older. And the same holds true for the for the the northwestern Hawaiian Islands. As you can see, the ages get older as you go further back, and of course they even get older as you go up the Emperor Seamount. This is a simplified view of the stages of Hawaiian volcanoes. You start out with a little blurb on the floor as the plume begins to start to bust through, makes a new conduit, and you start out with alkalic lavas. And this is sort of a result of probably crustal contamination as you're punching your way through. So you pick up the alkalics, you make alkalic lavas. Once you get going, you begin to get a really heavy main conduit going, and basically you start drawing from deeper in the core of the plume, and you start producing iron, silica rich, not silica rich, but just silica. You have more silica in them, deeper silica and iron, and you produce tholeiitic lavas with little alkalis contaminating it, because the throat is it's not getting contaminated, it's wide open. As time goes on, the throat gets more and more active, lavas being piled, pillow lavas come out, and then you begin to breach the surface. And so basically you have Luihi here, and I have a hard time believing that there is not something out further than Luihi. It may be erupting very, very infrequently, as you expect it would, from a new volcano that's just getting going. But to just go from something that's 200,000 to 400,000 years old to zero, I think there's at least one more out there, maybe two, who knows? But that's just me. So Loihi here. Loihi's going to be here in about 3,000 years, and of course this is where Kilauea and Mauna Loa are at the main tholeiitic shield stage. Pillow lavas underwater now being laid out with main tholeiitic stage subaerial flows. These are consistent. They build up about 95% of the volcano. This is where Mauna Loa, Kilauea are. Then we go to post-shield alkalics. Melting has slowed down. Your magma chambers in the upper part are beginning to cool and solidify. You're moving off the plume, and things have a tendency to stick around in the crust longer, and they become contaminated, and you start producing alkalic lavas again. However, these ones are slightly different. They do not have the helium content that gets released in the initial pulse of punching through the crust. I'm going to go into that in a bit. So the alkalics basically on top, the post-alkalic, post-shield stage have a tendency to be more like morbs. They become slightly more evolved, and they basically change, and they end up becoming a little bit more contaminated and start becoming alkalic from the surrounding crust, and just basically through differentiation and what have you. Erosion stages after that, you start building reefs, offshore platforms, blah, blah, blah. You see that on the east side of Oahu. East side of, northeast side of the east side of Oahu, Kauai on the east side. There's all sorts of areas where there's broad offshore barrier reefs, and that's the erosion stage, when there is really no eruption happening. Of course, the volcano itself begins to erode and subside. You get rejuvenation volcanism at some point later on down the road. Can be as little as a couple 100,000, but then it can be as much as a million. And then you have rejuvenation volcanism that dots some of the lower flanks, sometimes the higher flanks, depending what's up to the volcano. And you build things like Diamond Head or Punch Bowl or Kalapapa Peninsula on Molokai. Those are all examples of rejuvenation stage. And then once that, the final magmatic gasp, so you say, occurs, you have no more eruptions, the island continues to sink, you become an atoll with a coralline cap, then you become a seamount and you get subducted, and that is all she wrote. All right, so there's always been a sort of a question of whether the slabs are pulled or pushed. In other words, is there an underwater, a mantle flow under the crust, sort of like almost like sort of like a circular cell. In other words, the magma starts to the right, moves to the left as a big giant convection current, spreading ridge over here, subduction over here. And if it was pushing the plate along, you might expect to see these bend this way. In other words, The hotspot stays, but if you're getting pulled this way, or if you're getting pushed this way through this, you would expect um, the old conduits to bend the opposite way. That would just be my reasoning here. But if the slab is getting pulled and everything here is basically staying stationary, you would expect the conduits to bend back this way over time as they get cut off. And that is exactly what we see. This is a little more detailed. This is showing, the mantle plume and how it sort of drags a little bit. It actually drags a bit more than this. Again, this is oversimplification. You have old solidified upper magma chambers. As you can see in Mauna Loa, Kilauea, and the Big Island, you have some upper chambers that are still active. These ones have been cut off, so probably any melts that are occurring in these, rejuvenation or late post-stage otherwise, are generating down here somewhere. These have upper magma chambers. They are still active. Luihi, Kilauea, Mauna Loa, and then Mauna Kea back here in Hualalai. These chambers in Mauna Kea and Hualalai may be slowly solidifying. Mauna Kea slightly more. But you're not seeing a very large magma chamber up here. You're seeing what is left of something that's solidifying and cooling down as it gets pulled away from the mantle hotspot. All right, movement through conduits. Now, this one is showing a cross section. If you were to say, all right, so this is northeast and this is southwest, and you just took a slice right through the Big Island, this is what you might see underneath. Mauna Kea is actually into the page. It's back about 30-40 miles into the page. So this is the upper level magma chamber of the southwest rift zone of Mauna Loa. This is the upper two chambers of Kilauea. And then this is the solidified conduit and upper magma chamber of Mauna Kea. I put these in here. However, Mauna Kea still has a deep reservoir. It's probably not solidified yet, so you have a little bit of a reservoir down here. But the upper one has without a doubt shut off and has been solidified. Declement is basically, this is everything above is what the mountain has been built on. Same with Kilauea. Everything below is likely the crust. This is the main conduit of the plume. This is the main area down here of plume generation. And you can see you have a huge conduit coming up. It can spread laterally. It goes up into the Mauna Loa magma chamber and then shifts down one of the rift zones or summitly erupts. Likewise, you have magma come through it. It goes laterally, spreads up through conduit zones and fault zones, and of course supplies the Kilauea. I would imagine that this sort of goes over here too. I think that this is more spread out. However, there is a sill complex that goes laterally, and it does feed some of Kilauea. So similar magma chambers, but I think they're kind of separate. So you have major conduit coming up here, flooding the base of Mauna Loa in the middle of magma chambers. You produce eruptions. Sometimes it goes sideways. Kilauea likely has its own chamber as well. It comes up, goes laterally, spreads into the rift zones where like Pu'uo'o is, but you also have a couple of upper mixing chambers here. You have the conduit coming up, and you also have rift zone injection areas too. So there's a lot going on underneath these mountains. Now, plagioclase, it tends to be stable up above, whereas spinel is lower, and these play important parts on what you actually see and how the melts are generated. And this affects the chemistry, which I'll go into later. All right. So underneath, within the planet are these two massive large low shear velocity provinces, LLSVPS. And what these are, and it looks like there's three here. This is just part of this. So 2ZO is the same thing. So it's really only two. It's just the projection of the Earth right here. And this big area occupying the South Pacific, Central South Pacific Ocean, is an area of hotter material rather, that is chemically heterogeneous, much more so than the blue. The blue has a tendency to be more stable. Think of it as air. The air in here has volatiles, smoke, this, that, the other. The air out here, if this was air, would be fresh and uncontaminated for the most part. So you have an area in here that's rich in all sorts of radiogenic isotopes. You have possible surface crust that has made it down into the subduction zone and is basically creeping along the core, the outer core, and above this area where you have like possible areas of subducted slabs being melted and basically recycled, it's being basically uplifted. And at the boundary of this area here, we have the Hawaii hotspot, because you have something that's relatively stable here, you have something that is relatively unstable here, and when these two things mix, they create uplift and plume, just the way warm air and cold air do. And these are evidenced by here. Outside in the mantle plume, it's funny, the plume should be, this should be, the plume itself is red, but Mauna Kea source is in the blue, so it's kind of backwards, but forget about that. So the Mauna Loa plume basically has a tendency to be higher in radiogenic lead. Basically, this is saying this is some more primitive. It has recycled material in it. It has more radiogenic materials, whereas the ambient mantle here has been more stable. There isn't a lot of reaction going on, and the radiogenic lead is slightly less. So more going on here, more recycled material, more juvenile stuff, a hotter plume source being brought up. So basically, more reactions, more radiogenic lead. So this is a lot. There's a lot of instability here and a lot of stability here. And what's interesting, if you notice these dots, these are all known hotspots. Many of these hotspots have a tendency to occur on the peripheral. Now, of course, there are some that are in the center, don't get me wrong, but there's a lot of them, and a lot of the major flood basalts that have occurred over history are thought to have occurred on the peripherals of these. So when you look at these two things, you notice there's a cross section right here. We have a warmer zone, a zone of hotter melt, more melt here, and what you get is you have an enriched area of isotopes, lead, what have you, radiogenic materials, and it gets sucked up into the plume. So this is the unstable area, and this is the stable area over here. And these two plumes, basically, well, this is one plume, but there's two sides to it, and they produce different chemistry in volcanoes that have a tendency to be side by side. So think of it as Mauna Loa having one chemistry, Mauna Kea having another one. And these trends show up and go through the chain of volcanoes. So it's Mauna Loa, Hualai, Mahukona, Ko'olawe, Lanai, and then Ko'olau are the lower trends. And of course, on the northeastern side, you have Kilauea, Mauna Kea, Kohala, Haleakala, East Molokai, and then it stops. And then it starts showing up again somewhere near Kauai. And these two sides of the plume have a tendency to generate their own magmas periodically and inject into the plume with fresh batches, and that will be evident in a little bit. All right, so large low-level shear velocity zones, also called large low-velocity provinces, LLBPS, are superplumes characterized as structure in parts of the lowermost mantle, basically down by the core of the region surrounding the outer core inside the Earth. These provinces are characterized by shear wave velocities and were discovered by seismic tomography in the deep Earth. There are two main provinces. There's one under the African plate and one under the Pacific plate. Both extend laterally for thousands of kilometers. And here's the kicker. They are upwards of 1,000 kilometers in vertical from the core mantle battery. So Mount Everest is, sorry, my nose itches. Mount Everest is about 8 kilometers. These are like 1,000. So think about that. Just imagine a plume the size of Everest. Well, it's just, now imagine something, magnitudes much larger than that. I couldn't even fathom that. In any case, these two superplumes have been named Tuzo and Jason, respectively, after Tuzo Wilson and W. Jason Morgan, two guys that basically thought, that suspected the existence of these. The Pacific LLSVP is 3,000 or 100, basically roughly 1,900 or 2,000 miles across, and underlies 4 hotspots on the Earth's crust. and it's been suggested that there are multiple mantle plumes underneath. These zones represent about 8% of the volume of the mantle, or 6% of the volume of the Earth. So they are big, they are large, they are in charge, and when these things get pissed off and they decide to regurgitate pieces of the mantle, it causes very big problems, more problems you could ever want, and they're tied to mass extinctions. Oh, my nose. Ugh. All right, so Tuzo and Jason Earth superplumes. So what we have here is we have a cross section. This is either looking north or looking straight north or looking south, cutting the Earth in half. And what you see here is an internal structure of the Earth down to the, from the core out. You have an inner solid core, you have an outer liquid core, and of course you have Tuzo and Jason right here. And on the periphery of these, we have hotspots, plumes that pop up. Above Tuzo and Jason is areas of hot mantle that is rising and basically churning. These blue areas are areas where subducted cold ocean crust as slabs is descending into the core, and what it does is it piles up right around here, and then it begins to migrate laterally until it eventually heats up and gets sucked up into one of these. Now, within this this plume, there's an area called the ULVZ, and this is an ultra low velocity zone, meaning this is even hotter. It is enriched with incompatible elements and radiogenic materials, and this is one of the sources of the Hawaiian hotspot plume. And here it is right here. I put it in. This is plume generation zone is PGZ, and you can see here is the Hawaiian hotspot going up, and here's Hawaii right here. So this gives you an idea of how these work internally. You have most of these, like I said, the Hawaiian hotspot is right here on the periphery of Jason, and it's mixing with ambient mantle here, and of course the unstable recycled crust and whatever else has been dragged, and whatever else is in this particular batch of the whatever else is in this plume. This plume is, like I said, it's chemically heterogeneous. It's got all sorts of different things in it, as opposed, clean, fresh air here, contaminated and reactive air here. Just think of it as that way. Stable, unstable. And if you want to look at it here in a cross section, this is more detailed. Here's the slab going down. The slab generally, sort of ends right here, but there's a whole bunch of stuff that ends up going much deeper. The residuals of the slab, it goes down, it begins to heat up, it begins to melt, and then it travels laterally. And as initial melting, you would produce an ultra low velocity zone. This is some of the hottest. This is enriched material right here. And then, of course, it begins to descent back up as it starts to mix with the LLSVP. So this is where the action happens. And as the material, even though it's hotter, begins to heat up, even though it's denser, if you put enough heat into it, it will become a buoyant, and then it starts its ascension up. And in this case, it's producing a giant lip. In our case, you just substitute this for the Hawaiian hotspot. The lips are much more devastating. Like I said, they cause all sorts of problems in the geologic record, extinction events, but the message is still the same. You have crust going down, you have melting, you have parts of the slab going down to the base of the core, moving laterally, remelting, generating a new batch of enriched source materials, and then it ascends back up. Now, one other thing with this is, if you notice, you have a slight bulge over these, and that is because these things are so big and so hot that they actually flex the crust. So the Earth is a geoid; it's not completely round. This is just another hot spot over here. So Africa here, and then Pacific over here. All right, superplumes. This is what they look like within the Earth. So this is the shape of the Earth right here. These are the superplumes right here. They're not uniform. They're very chaotic looking. They have a tendency raise in areas, and it's just basically a very large area of material within the Earth that is trying to make its way up, and that's what you see right here. So there's one on each side. I guess they kind of balance themselves out. All right, large low shear velocity provinces, LLSVPS. Like the Pacific LLSVP and mantle plumes, they represent distinct features within the Earth's mantle and may differ significantly from the ambient mantle surrounding them. So this is just something I said, that the large low shear velocity LLSVPs are much different than the areas around them. So in other words, the ambient mantle is sort of like the house, and then the LLSVPs move into the house and occupy a couple of rooms. But as a whole, the ambient mantle, the stable area of the mantle within the Earth, surrounds these plumes. These plumes are within it. So you have an area of instability and within an area of stability. And here's the big differences. So structure and location. The ambient mantle, this refers to the average mantle material that surrounds the LLSVP and plumes. The structure of the LLSVP is a massive structure located near the core boundary CMB. It's thousands of kilometers wide and 1,000 kilometers tall. The plume produced between the two is a buoyant, upwelling area of hot material that rises from the LLSVP, actually between the ultra-low zone, which moves into the LLSVP, and then it rises and potentially reaches the Earth's surface, forming hotspot volcanoes. The temperature, the ambient mantle is considered to be relatively average temperature, so the Earth has a geotherm, and for every how many feet you go down, you expect to go up X amount of degrees, and the ambient mantle is basically what you'd expect. You know, for every 1,000 feet it goes up X amount of degrees, and it plots pretty much right where it should. Now the Pacific plume is significantly hotter than the mantle, and they can tell by it's evidenced by the low shear waves. In other words, when we have earthquakes or explosions or anything that travels through, sound waves or whatever waves, as they go through, the colder the crust means the tighter the atoms, which means the quicker those shear waves move. But if you have warmer crust or liquid, they have a tendency to slow down and maybe even just stop. And so when we see these areas where there's just very very slowed down shear waves, we know that that's either warm or there's melt in there. So the mantle plume is buoyant and hot, and it rises off the LLSVP, and it's associated with higher temperatures. Okay, so the composition. Now, generally, the ambient mantle is generally presumed relatively uniform composition, primarily of ultramafic silicates, yes. However, some models suggest localized variation fluids, but that's the subduction processes. Well, what that is saying is that there are areas in the mantle where pieces of crust just delaminate and drop, which means they get assimilated. They drop down, they become heated, they get assimilated. There's pieces of continental crust that do this, pieces of oceanic crust. So as even though it's relatively stable, the ambient mantle, there are things that can affect it. It's just not nearly as unstable as the LLSVP. Again, the composition is debated, but generally believed to be thermochemically distinct, means there's all sorts of stuff going on that's different than it has a proportionally higher intrinsic density, means it's more dense. And in addition to being, so because it's hotter, the density is basically zeroed out and allows it to, you really heat something, you get it hot enough, even though it's denser, it will still heat and other things that, the more you heat something, the less dense it becomes as a rule. The mantle plume is, if you mix these, is composed of material entrained from the LLSVP, potentially with distinct chemical signatures compared to ambient mantle due to the SVP concept. So in other words, the plume, between these two, you're going to have LLSVP materials and you're going to have ambient mantle characteristics. And those are the Loa and Kea hotspots respectively. So here are the Loa and Kea trends and sources. This is going back to what I was just saying. You have the LLSVP here, you have the Hawaiian hotspot here. And if you want to break, so you have part of the material going up here, part of the material going up here, and then if you blow this up, this is what you see. You have material from the plume here getting sucked up, and then you have material from the ambient mantle getting sucked up here. And you have Mauna Kea here and Mauna Loa here, and that is really the simplified version of what is going on. This area near the boundary is mixing, it's sending material up. Anything in this color here is warmer, maybe more liquid. Anything here is colder. So you see a slab coming down here, a slab coming down here. And anything red you see rising, and that makes perfect sense. This is a huge plume, the Hawaiian hotspot, cross section from A to A prime. You get one side being Loa, one side being Kea, and then this is a more detailed breakdown of it. Now you can see both sides. You have the Loa side here, where you have basically chemically heterogeneous materials. You have stuff that is probably recycled materials from old oceanic plates, possibly even continental materials, possibly even surface materials that have been subducted and brought down, and is represented by these blobs. And then you have the ambient mantle over here, where it seems it's relatively straightforward, and you don't see a lot of different materials getting sucked up. So that's represented by just the straight red arrow. When these things combine, you have mixing right in here, and volcanoes that are near the border have a tendency to go either. They can have a little bit of both, and I'm going to show you that in a minute. So Loihi's right about here. This is enriched Mauna Loa. It's represented by the blue stuff, and every time you get a blue blob, you have enriched materials, and so that's why and these enriched materials has more radiogenic material than this, and that's why the lead tends to be higher. Down here, again, this is the Pacific megaplume. This is the ultra low velocity zone. This is the hottest point of it, and boom, the hotspot, the Hawaiian hotspot, is right there on the edge of it. And so you have Loa materials here, Kea materials in the square outside. Low materials, again, inside the plume, right within the ULVZ, and then you have Kea materials out here in the ambient mantle, which is outside the red zone. So you have Mauna Loa magma generation in the red, Mauna Kea magma generation in the clear. Volume estimates for volcanoes. So this is something that I have always wondered about. Why is it that some volcanoes are so much bigger than others? It seems, people, I've been told that, they all end up becoming the same size. I never believed that. And so this is a great map that sort of explains that. So each one of these are thought to be volume estimates of the volcano. This is the Loa trend right here, and this is the Kea trend in red and yellow. And what's interesting is, so here's Mauna Loa. We know it's the world's largest mountain right now, and rightfully so. It gets a big giant circle. Kauai, probably around the same size. Waianae, surprisingly very large, as well as Haleakala. That is another one that we know is very large. Now, what this is telling me, this is PB ratios, radiogenic. And as I said earlier, anything within the Mauna Loa side has a higher amount of radiogenic materials from recycled crust being sucked down. Just has more reactions. The Kea side is more the ambient mantle. It doesn't have as many, it's more stable, it has less radiogenic material, and so of course it plots slightly lower, so the reds are slower. But what's interesting is each circle represents the composition contribution to the volcano. So in other words, right here, the older part of the Kauai volcano had Kea magmas, generated magmas, but the younger part had Loa. So somewhere in here, the composition of this volcano changed. In other words, it got an injection from a Loa trend. So in other words, this sat right on the border. So for a while it was Kea, but then it became Loa. In a very long period of Mauna Loa, the last 5 million years, has taken over this trend all the way down to Loihi. But something really interesting happens right here, where you go from light blue to dark blue, and what this is this is an injection, or an injection of Loa enriched material from the UNLV zone that pops up in the late stage of the Ko'olau. So you had average Loa compositions from here to here, and then boom, you get an injection, you get heavily enriched material, and then it basically these volcanoes are showing enrichment here, and then as that injection wanes or the materials get diffused, you go back down to average radiogenic levels for Loas, and you can see that right here. Boom, about 200 miles off the hotspot, late stage Kilauea, you have an injection of highly radiogenic material as compared to the rest, and that is the thought to be a plume injection. Now, of course, the Kea trend, you might have gotten a plume here. This probably periodically gets refreshed, but as you can see here, it had something here, it had an injection, and then there's really nothing. We don't see much of anything here. We don't know. There might have been something out here, but it evolved from here to here over time, and of course you have evolved Mauna Kea magma generation to the point where you actually get the end result right here at Kohala, and then you have a new batch, a new injection here. So injection, evolved magmas, really evolved magmas, and then you get an injection when Mauna Kea is over the hotspot. So these are the two trends. You have the Kea trend, basically less radiogenic material, and then of course you have the Loa trend, more radiogenic material, and they can flip-flop apparently. You know, they can inject the same magma chamber. At least it looks that way. This evidence here suggests that. All right, so to look at this in a little more detail, what I've done is I've taken this. This isn't as confusing as it looks. It just takes a little bit. So as I said, the older Ni'iau Kauai system had Kea lavas. We just saw that back on this right here. Boom. But then we get an injection into the Kauai volcano area of Loa, and then you have, or it switches over to Loa rather, and then you get a massive injection or a enriched injection of Loa material in the late stage of Kilauea, and then you get another injection here of slightly less mafic materials here around the time of Lanai and Kilauea, and then of course it goes back to average Loa. Mauna Kea seems to be relatively stable. You had an injection here, but then you don't see it show up back here. So this has a tendency, it basically evolved. So right here, this stage is represented by here. You have Loa, you have earlier Kea trend, but now you have Loa coming in, and this is basically average Loa lavas. You have the capture zone and then the mixing zone right here. So this is the plume melting zone, and this is the magma capture zone, and this is what supplies the volcanoes. So average Loa in light blue, but as you can see, there's an enriched component coming here and another component coming here on the way up. So the Ko'olau Makapu, this is late stage Ko'olau, not the main phase. The main phase was still in the blue. You get an enriched injection of radiogenic materials, fresh materials from the Loa side from the LLSVP, represented by this blue here, and we saw that chemically here. You can see there's an injection because the radiogenic, the lead goes up. So now you've got Loa materials as the base. You have enriched materials for the Makapu'u, late stage. It's still tholeiitic though, magmas in the Ko'olau. And then outside of that to the right, you still have, or to the northeast, you still have the possibility of Kea lavas. Now, when you get to West Molokai, we go back to average Loas right here, and of course the Kea trend is going on with the East Molokai volcano, but then another injection happens. You have near Lanai in Ko'olawe, you have an injection of green. Well, it's represented by the green here, and you can see you have the Kea trend of West Maui, you have the Loa, average Loa, but then you have this newer batch of green stuff here. This stuff has higher strontium. And strontium, it has higher strontium and lower radiogenic material. Not much, but slightly. And I'll show you right here. Actually, it doesn't show up on this one. It will on another. But anyways, this right here is slightly more felsic, meaning that we think that the enriched Loa material here that got injected right here was more mafic. We think that this has more felsic sediments, maybe some sands, maybe some continental material. In any case, this is slightly more felsic and changes the chemistry, and you can see that in the Lanai Koholave area. And then once this passes through and gets and dragged in the hotspot, and the volcano gets dragged up the hotspot, and of course the more felsic materials, or the less radiogenic materials rather, we go back to average loas, and you see that in Mahu, and you see that in Mahu Kona, Hualalai, Mauna Loa, and of course Loihi. So these circles plot the types of volcanoes in the chain. So you know, in Kauai you've got basically a Loa with a little bit of Kea left over to, you know, basically north and east. You have an injection into the Kilauea volcano, but yet you still off to the north and east you have Kea lavas. When you get to West Molokai, you have the West Molokai volcano and the East Molokai volcano, which is a Kea trend. When you get to Lanai, you have Lanai and Kolave, which are lower trends, but of course you have Haleakala, West Maui, West Molokai, and West Maui, which are Kea trends. And of course on the Big Island you have Mauna Kea and you have Mauna Loa. Mauna Kea is a Kea trend, and Mauna Loa is the lower trend. So radiometric map of plume core showing Loa and Kea trends. All right, so like I said, we had some Kea action going on up here, and as time went on, the Kauai magma chamber switches from a Kea trend to a Loa trend, and the Loa trend continues all the way down through here. But yet the Kea trend seems to go dormant here, or we don't see any action from it, but then it shows back up again on the East Maui, West Maui, Haleakala, etc. And geochemically, or by lead isotopes and geochemistry here, we can see what happens. You have a trend from here to here. Why? Because this right here is telling us there is an injection of Loa materials right in here, and it pushes the radiogenic signature of lead up, and it peaks. So you get the plume injection, you cross from Kea to Loa. You can see it in the lavas right here as they begin to get progressively more radiogenic, and then there's a peak right here at the Makapu'u side of it. So in other words, you have an injection, it goes down, and then you get another massive injection here of very, very enriched material, and it begins to drop again, and then you have another injection here of slightly less radiogenic, but it's probably more evolved recycled material, and then of course the trend goes back down again. So injection of Loa material, evolution of Loa material, injection of Loa material, evolution of Loa material. So down here is average, but these are 1, 2, and 3 injections. The Kea materials, maybe one here, maybe one here. Hard to say. So we have an injection of Kea here, a downtrend, and then an injection here, and then maybe a downtrend there. But these are the volcanoes showing all of the Loa and Kea trends. And as I said, everything to the north and east is going to be more Kea. Everything to the south and west is going to be more Loa. And you know, the plume is probably, you know, the LSVP border is probably somewhere under here. And if you want more chemistry, this is where you begin to lose your mind. And I did numerous times going over this. You know, in a personal note, when you're doing something like this, as you make this lecture, you have a tendency to have epiphanies, and you start adding. And I always use, you know, I always use the movie Jaws for something that's way over budget, much more difficult, but the authenticity of it required this type of work. Now, I'm not going to put out a Jaws, but what I am doing is something very similar to the way he did it, is that I am learning something, and the more I learn it, the more I basically improve it, and I redo it, and I get a better grasp on the material, and I get a better idea how to explain it, and then I can tell the story better. So through this whole thing, I periodically have had to make new charts. I've had to find new charts. I had to back up because I start to understand things more and more and more, and that's what's amazing about doing this. So, you know, looking at this chart in front of us, you know, you can lose your mind, but it makes sense if you put in the time. And I believe I've made sense of this. So, hafnium, niobium, strontium, and lead are our friends. They will tell you a lot about where these magmas come from, how they got there, and their journey, and what went into them. So, we've all become very familiar with this, the Mauna Kea trend. So the leads, as I said, very non-radiogenic, well not non, but less radiogenic, and then you get a pulse right here. You get one here and one here. And you can see it isotopically, you can see it right here. The leads, you get enriched material right here, boom, goes right up. Then you get another injection, boom, but it has a little bit more advanced or evolved materials. And guess what? The strontium proves that. Lead and strontium and niobium have a tendency to go in opposite directions. So here's the injection. Here's sort of the evolution of it. But if you look down here, you notice that this one is shorter than this as far as strontium goes, and that's because more evolved materials, more evolved recycled crust has a tendency to build up more strontium. It is the decay product. So you go from more primitive stuff here to a more advanced, more evolved sediments or magma source here, and it's proven by this. So you would expect if high radiogenic, more evolved, but if you go down here, you would expect this because the strontium is going to start. So in other words, lead builds up more in an enriched magma, but there's less strontium in that. If it's really enriched, it's more primitive, and it's more juvenile, which means the strontium has not had time to build up, but the lead has. So the lead will be higher here and lower here, but the strontium, because this is more, it may have continental materials, more evolved, you're going to have less. As far as strontium goes, the more primitive and the more juvenile injection is going to have less strontium, and the more evolved, and say, if you have more quantum or felsic stuff, you're going to have more strontium. I mean, it's older. So you're going to have more strontium in here, which means it plots higher. And that is proven by these two graphs here. They're basically are inverses of each other. Now, if we go down to the niobium, niobium also has a tendency to be lower in high melts. And basically, this injection right here is one of the highest melts. In other words, we think it's close to 80% melt, which is off the charts. Usually it's like 25 to 30 is normal. But when you have an incompatible element, think about it. If you have something that's incompatible, and you have so incompatible means that when the melt solidifies, you do not take any of that material out. So in other words, if you have X amount of niobium in a melt of 10%, it's going to be more niobium in the melt than it would be if you had a melt of 40%, because 40% melt means that you have the same amount of niobium, but it's dispersed, there's more melt. So the more that rock solidifies, or the more minerals taken out, the more that magma becomes concentrated in niobium. So if it was very liquid when it was loaded with it, when it got injected here, you would expect to be diluted, and of course it is. It is slightly diluted. It goes down. Here you have less melt, probably 20 to 30% melt, but here you have you have a much higher percentage of melt. And I believe it's up to 80%, and if that is shown by the downdrop because when you have more melt, you have niobium basically in that melt gets diluted. So it's like taking salt and put salt in a glass, put a cup of water. Even though you have the same amount of salt in it, if you add another cup of water, that salt's going to dilute. That's basically what we're saying. And it's the same thing here. You're going to dilute the strontium too. Of course, there's less strontium because this area here is slightly more evolved. And the hafnium does the same. Niobium and hafnium follow the same suit. And you can see that niobium is also, or hafnium is also going to be diluted, so it drops during an enriched injection with high melts, and of course the strontium follows suit. So I hope that makes sense. But this area right here tells the story of sources. In other words, what you take away from this is that you had material get heated from the core, You had stuff that was probably part of it was recycled crust, maybe even continental materials at some point, pelagic sediments, and all of a sudden it melted, you know, from 30% maybe 20 to 30% to 60 to 70%, maybe 80% melt, and uh, that melt was loaded with radioactive and primitive isotopes, meaning the lead goes up, it's loaded with it. Um, but again, when you have more melt, you have the same amount of incompatible elements, which means it dilutes and it sends the amount that's in that particular melt, it dilutes it, and basically the concentration goes down. And that's all this is saying. It's just showing that you had an injection of very hot material, something that was enriched. It evolved. You had a second injection here of more evolved materials. When I say evolved, more felsic, and that is just being shown beautifully by these four graphs right here. So enriched injection, more primitive, slightly more evolved, but they behave, and incompatible elements get diluted, which means they go down during the injection. And as the magma begins to solidify and erupt, and you begin to take out the melt, the trend is for it to start going back up again, and it does. All right, here we are. So this is the guts of it right here, and what this is saying. All right, so higher cerium, niobium, iridium, niobium, and blah blah blah, and higher hafnium for a given niobium and enriched loess elements has been used to infer their sources likely contain recycled oceanic crust and pelagic sediments. That is what I've been saying the whole time. So higher strontium, more recycled materials, maybe even more felsic recycled materials. So as I said, when you have more melt, these two get diluted. If it's more mafic, these two have a tendency to be a little bit higher. More felsic, more evolved, the strontium is higher. So anyway, however, the Ko'olau Makapu symbols are distinct from the Lanai and Ko'olavi samples, especially in the hafnium, niobium, as well as the leads. And in SiO2, CaO, Nb, Sr, allylatum, and cesium and lead. Given their high SO2 content and lower cesium, lead, niobium, high strontium, and high lead, we hypothesize that the Ko'olau Makapu'u compositions result from the incorporation of a higher proportion of recycled continental materials. Bang. So, as I just said, this right here is representing possibly more continental material, more felsic material. So basically, you know, you're taking a piece of the ocean crust and eating it up or assimilating it, and so the lower crust is more gabbroic, which means it's more mafic, which may explain why we had a more enriched source. And then the second source, the green source, right here, maybe further up in the actual slab when you're getting, you know, carbon. Basically, ocean crust gets more felsic the higher you go up, just because of materials that get rained down in the ocean. Sediments get washed out, what have you. So that would account for this higher strontium reading. This does not exclude the possibility that recycled plagioclase-rich ocean crust is also present in this source, especially given the heterogeneity of enriched Loa compositions. Importantly, the lower mantle reservoir is hypothesized to contain enriched heterogenees, i.e., or e.g., the Pacific Super-plume. They may consist of many different materials of numerous origins. In other words, saying there could be a lot of other things that we haven't even begun to decipher yet. But in any case, this isn't going to make a whole lot of sense, but this one does. I mean, the hafniums are basically saying, hafnium over niobium, saying more mafic, you're going to get a higher concentration of hafnium, niobium. More felsic, you're going to get a slightly less. And so the Loa basically is here. It looks like, I don't know if it's K or not. Looks like there could be a K here, but it would be lower hafnium, although it does have a fairly high amount of niobium. So, so enriched Loa has higher hafnium. Yeah, that makes sense. Okay. So you look at this one right here. This is sort of, where you're kind of getting an idea of what's in the mix. So the Kea up here is down, I'm guessing, these are sediments. You have sand and clay, you have pelagic sediments, you have turgid. So this is from land, this is going into water, these are sand and clays going into water, and these are chert. And over time, these have a tendency to plot, basically moving into this area right here. So these are potential sources for what's feeding the Loa and the Kea plumes. And so the way I look at this is, 2 billion years ago, the niobium was concentrated over here. But over time, it's begun to drive itself more towards the right, as has a lot of other things. And so these are basically saying that, so this is your Loa, this is your hafniums, and this is your Keas, and this would be ambient mantle. It's slightly not quite as steep, whereas these have a tendency to be slightly more steep. All these are saying is that these materials, the Loa and the Kea materials, have a tendency to be a combination of a lot of these different things here. So that's what you're getting out of that. It's quite a it's quite a map. I mean, quite a plot right here. Now here, you're seeing a plot of enriched Loa, average Loa, and then Kea up here. And it makes sense because it's sort of going up towards depletion, and that makes perfect. How does the plume influence stages of Hawaiian volcanoes? For Hawaiian volcanoes, samples niobium over yttrium and zircon yttrium can be used to verify the volcanic stage of a given sample because niobium is incompatible and sensitive to the degree of melting. Tholeiitic basalts formed during the shield stage largely which create a larger degree of melting that build 95% of the volcanic areas have lower niobium for a given zirconium rather than alkalic basalts formed during the post-shield. And that's because of the degrees of melting. More melt, more dilution to the niobium. So we know that the tholeiitic stage has high degrees of melting. Therefore, the niobium in there is more diluted. And then during the alkalic stage, there's less melt, and this becomes more concentrated, so you have higher niobium. And it says right here, more melt, less niobium, as it is called, due to dilution. Shield stage basalts are formed from the hottest part of the plume and have experienced the least contamination upon ascent through the crust, and are most representative of the stages of average composition of the mantle source, thus lower potassium and sodium and low niobium. This is saying that the throat is wide open, it is absolutely going full bore, and we're not touching the sides as much, so we're not getting as much contamination. Now the alkalic rocks that are produced during the post-shield, pre-shield, and rejuvenation stages are representing the cooler parts of the plume because the plume has moved off the hotspot. And then in the case of rejuvenated rocks, which are formed up to 1 million years after the shield stage is complete, as such, it is really important to get these amounts of niobium and figure out what stage the volcano is in, because a higher niobium is basically saying you have less melt, which means, and if you have some alkalics in there, which makes sense because it's a cooler part of the plume, it's sitting in the chambers longer, it's not getting refreshed, and it's becoming contaminated. So the higher niobium here tells us that this is likely something that's off a cooler part of the shield. There's less melt, it is becoming contaminated, and that's why it's important to verify what stage of the volcanoes you're in and how the plume is going to influence that. Recent work suggests that recycled materials are likely present in the mantle sources of both Loa and Kea trends, along with prima-like conditions, which primitive mantle for the Kea trend volcanoes, creating various heterogeneous in each of these large-scale, long-lived Hawaiian geochemical trends. Numerous studies have linked the surface expression of the Loa Kea trends in the deep mantle. On the lowest side, the plume might sample material scored within the Pacific, the LLSVP, which is located to the southwest of the Hawaiian Islands. The Pacific megaplume is a large structure at the core mantle boundary with thermochemical properties distinct from the surrounding mantle. We've gone over this. And it could be a repository of subducted surface materials or near surface materials. A compositionally distinct ultra-low velocity zone at the edge of the Pacific LLSVP has been hypothesized and is considered to be the source of enriched Loa compositions. Ancient recycled materials may be variable stored in either of these lower mantle structures, and the chemical heterogeneity of enriched Loa, its small volume and relatively short duration, indicate that these stored materials vary in composition size. Therefore, both LLSVP and ULVZ are probably chemically heterogeneous on many spatial scales. And I agree with that. Both of these, the LLSVP has all sorts of stuff in it, which is going to be chemically heterogeneous. And then you have the enriched area, you're getting a very hot, you're getting a dose of primitive magma and heat from the core. So the variations of how these mix, and then you add in ambient mantle, I mean, all sorts of different reactions go on. So yes, that is putting it very mild, the heterogeneous nature of these, of the LLSVP and the ULV are huge. On the Kea side, the Hawaiian plume source is thought to be consistent of materials from the lower mantle and outside of the LLSVP on the northeast side. Yes, this is consistent with Kea volcanoes have similar isotopic values to the prevalent mantle, which is thought to constitute the ambient lower mantle. However, work suggests that there is even some chemical heterogeneity within the Kea trend. So, again, Kea outside of the mess that is the LLSVP, and of course the isotopic values show that it is lower with radiogenetic materials, and it has a signature very close to the prevalent mantle, which is the ambient mantle. All right, geochemistry in various volcanoes. So the 206, 204 to the SiO2 is basically saying that, all right, this is a more stable isotope, but during the open throat tholeiitic stage, you're going to be pulling up some of the deepest parts. You're going to get a good amount of SiO2 in that core, and it's spelled out perfectly here by saying, yes, we have higher SiO2 content in fresh batches because it has not had a chance to cool out, because it's one of the first to cool out. So the more primitive, the more hot, the more deeper the magma source, you're going to have a higher percentage of SiO2, even though it's still tholeiitic, because over time, during ascent, you may start melting out SiO2, as it is one of the earlier, I'm sorry, it's one of the last things to come out. However, it has a tendency during the main plume stage to draw higher percentages of it. So here are the volcanoes. As you go down, the Kea trends have a much lower proportion to the melt because they are not drawing off enriched materials. They're drawing off ambient mantle, which has a good amount of SiO2 in it, but not like the deep injection of the from the LLSVP. And if you look at cesium over lead, you see that that enrichment has a tendency to go off to the right when compared to cesium. The Loas have tend to be much more enriched in the 208, 206 as opposed to the Keas, and that's obvious right here. The strontium, this is also showing us that we have more recycled materials as opposed to the Kea. So strontium indicates recycled materials. And of course, it also has it has less niobium as well. If it's more mafic, it's going to have more niobium. And of course, over here we have the Kea materials have less strontium and slightly more niobium, and that is because they have a tendency to be they're ambient, and this is a more consistent, and it's not quite as diluted. This is more diluted. This is not. I mean, it's diluted, but again, your niobium concentrations are going to be slightly higher. And then this is basically a comparison of your other volcanoes. And again, these so the Society Islands and Pickering, which is down in the I believe the Leeward Islands. This is just basically showing that you have lower niobium and more MAFE. So basically, the strontium, this is more recycled materials. This is not recycled materials, but at the same time, this is a lower degree of melting compared to this. Compositions of parent magmas. This is a mess, but the gist of it is purple is abyssal peridotite, blue is peridotites on the mantle, and beige is phenocrysts from the mid-ocean ridge basalts. You know, three very distinct things. And as it turns out, the magmas of Hawaii seem to have a generation of all of these. So you got peridotite from the mantle, you got abyssal peridotites, you know, from the crust, and then you have mid-ocean ridge basalts that are all thrown in there. I'm not going to go into huge detail because, I mean, just staring at it makes you crazy. All right, so niobium in the earth and in magmas. Deep source mantle injection, particularly of mafic iron and magnesium-rich melts, could potentially lead to a relative lowering of niobium concentrations in the resulting rocks or magma. Here's a breakdown of that rationale. Niobium is incompatible. It is a highly incompatible element during partial melting of the mantle, meaning it tends to preferentially concentrate in first in melts, and the first melts that form. So mafic melts and mantle sources, mafic magmas often originate from the partial melting of the mantle at relatively high degrees of melting compared to more felsic magmas. Niobium concentration degrees of melting, because niobium is incompatible, the concentration of niobium in a melt generally decreases as a degree of melting of the mantle sources increases. So in other words, because it's incompatible, the concentration of niobium melt decreases as there's more melting. There's like a set amount. Again, salt in 1 cup. The amount of salt in 1 cup is more than the amount of salt in 2 cups. Deep mantle injection implications. If a deep mantle source injection brings up melts derived mostly from a large degree of melting of mafic-rich sources, these melts could lower incompatible melts like niobium compared to melts generated from smaller degrees of melting. So that's just basically saying that, again, niobium is a great indicator, saying that, you know, the more melt you have, the less niobium you're going to have in the concentrated. So niobium and lead isotopes, these basically tell they're kind of inverses of each other. So when you have a injection of high melted materials, the niobium goes down. You can see it right here. Basically, you know, your niobium is more concentrated up in here, much higher in the Kea trend, much lower in the lower trend. And that's because there's enriched elements. And when you get a massive injection of lower trend enrichment, it brings down the hafnium, and you can see it right here. Conversely, that same injection brings up a lot of radiogenic material. So of course, that rejection is going to raise radiogenic materials. So that's why you can see lower niobium equals higher radiogenetic materials if there's a lot of melt. So deep mantle source, mantle injection lowers niobium due to mafic properties, and if there's a lot of melt, it is due through dilution. Deep source mantle injection increases the 208 lead ratio due to decay products from old recycled crust. Boom, there it is. So this is a niobium map, also with a plume map. This is I think this is at 150. And what this is saying, this is kind of like a flux map. So right over the hotspot, you have basically a high flux of the plume, which is represented right here. And of course, it drags. You have residuals over here. But what this is really telling me, and what we just said, is that near the source, with the plume location at the surface, you are going to bring up and dilute, because Mauna Loa has a much higher degree of melting. The niobium is going to be diluted, and of course it's shown here is going down over under Mauna Loa, and of course that is what we'd expect. Now over here we have a Kea. This could be this is bimodal, so it means it's got two peaks. This could be the Kea trend because it has slightly more niobium. I'm not 100%, but I'm seeing bimodal peaks here. So one with very low niobium, one with sort of low niobium, if, and compare this to everything around. So now the center of the plume might be here, but the drag effect is here. That's the way I would kind of look at this. So this is where the plume is really basically regurgitating a lot of material under Mauna Loa, and it makes sense because if it's really, this is the highest degree of melting, which means you'd have lower niobium. Now there's a good degree of melting here, but because the Kea trend is not quite as loaded with radiogenic materials, you would basically you might have or the degree of melting is not as high. You're going to have a higher amount of niobium. So plume location, your surface with niobium anomaly revealing its location. Lower niobium and runnel maybe from the lower trend plume because it has higher degree. All right, possible areas of magma mixing under select Big Island volcanoes. All right, the pink right in here that I put in, this is where your shield, this is your main shield zone right here. Outside the pink is where the pre-shield and the post-shield production zones, with only 2 areas of mixing, unlike the main stage where there are numerous. So in other words, main shield stage has numerous mixing zones and magmas here. You can see it under Kilauea. You can see it here under Mauna Loa. Loihi and Hulalai, however, do not have upper level magma chambers, or if they do, they've probably, well, this one just hasn't really had a chance to get going yet. This one is probably beginning to solidify. Now, down in here, this is sort of where the action goes on. So you're bringing up peridotite with eclogite. You melt the eclogite first. And then you have a melt plus peridotite, which is going to equal a peroxenite. Then you melt the peroxenite, and then you remelt the peridotite, the second phase, and this is where you generate most of your magmas right here. I'm not going to go through this in huge detail because this is heavy duty stuff. But the gist of it is that this is where you get your melt. This is where the melting is going down. So you've got melting here. You have pure melt here, not pure, but you have a high amount of it, and then as you ascend, you induce more melting, and then basically you come up through the crust. You have chambers where you mix in, and then you pop out. The older volcanoes do not have as many mixing chambers. In fact, some of them are probably down here at the base of the crust, and therefore these magmas don't get mixed up quite as significant. This is the plume under the Big Island. This is basically what this is saying. This is what the plume looks like right now. You got at 1400 degrees on primitive about 2% of melt. Over here you have about 12% of melt. Now here you have about 27%, and this is the hottest part of the plume right in here. So this is represented by here. Now Mauna Kea right now is probably in very, very low. So is Hulalai, 2-3% melt, whatever. But if you go back in time, Mauna Kea was once here in relation to the hotspot, and its plume melt was huge. It's the same thing here. Loihi, when it eventually gets to this point, its plume melt is going to be going up. Kilauea is right here. It's got a high plume melt. Mauna Loa right now is a high, and of course, this right here is considered not just the hottest spot, but this is also the highest degree of melt. And within this, we think there's a good amount of old recycled crust right here. So this is where you have melting, this is where you have mixing, and this is where you have magma generation right here. And of course, these pre-stage and post-stage lavas, shield stage, are in the cooler areas, and they do not have nearly the amount of melt that you do when you're in here. So this is a cross-section of a typical Hawaiian volcano. You have the thallitic stage, you have the pre-shield stage, which is calic, you have the crust, you have the downbowing, you have post-erosional, or rather, post-erosional rejuvenation eruptions. You have a shield stage, a post-shield stage right here. So these are just basically a simplified view of these stages of, and of course, 95% of the volcanoes here. So alkalic, alkalic, and then these are alkalic and silica undersaturated, which is pretty much the definition of rejuvenation volcanism. So, Hawaiian lavas from select volcanoes. This is a great map to, this diagram is really, it's kind of the bread and butter for what we use to plot our chemistry of our volcanoes. So during the main shields building stage, we have low alkalis, we have a tholeiitic main shield building stage, and almost all shield building tholeiitic lavas plot right down here in the basalt area. They have between 45 and, we'll say 55% SiO2. They're very fluid. They don't have a lot of alkalis because they're not being contaminated. So almost all, you can look at them right here. You got shield. These are all shields. They're right down here. And they stay relatively uniform for 95% of the volcano's life. You get to the pre-shield and the post-shield stage, you have alkalic contamination from probably the crust that it needs to punch through, or from laying, or for staying residing in magma chambers for a long period of time, and thus assimilating some of the characteristics of the actual crust. And then when you get to rejuvenated lavas, you're going to go way down in, they become silica undersaturated, therefore you don't have quartz. Or if you did, you'd have very little of it. You start forming other minerals like melilite and nepheline, and these plot way over here. So they have high alkalis, very low silica. Now these are interesting. These are from West Maui. These are post-shield lavas. They are tracheites, bemerites. Very unusual, but on this island they seem to be very prevalent, and I think it has something to do with the fact it's a Kea trend. It seems to be, I don't know if there was an injection of some sort, or that magma differentiate over long. I don't know what the reason why it came out like this, but the late stage, post-stage, shield stage lavas of West Maui, especially on the northeastern quadrant, are just loaded with tracheites and bemerite lava flows. So that, I don't know the exact reason for that, but it'd be interesting to look into why that, it seems to be more there than anywhere else. Again, same diagram, but I've just basically cleaned it up a little bit. I've put in some of these are pyrite, muggerite, and bemerite are post-shield lavas. Your tholeiitic stage stays right in here, your post-shield stage here, and of course your rejuvenation stage is here. Sometimes going into ultramafic, silica undersaturated. Remember that bemerite is a more felsic, it's got higher SiO2. And of course mafic, this is where the majority of your shield lavas are from for Hawaii. All right, shield stages of Hawaiian volcanoes. This is going to be our next video. I'm going to stop here. This has been, I hope that this works, because I'm going to probably lose my mind if it does not. This will be the third time I record this. This was a very geochemistically heavy part. The ones following this are not, but I really needed to hammer that stuff home in order to make my arguments. And it may be a lot of gibberish and difficult to understand now, but trust me, when I come back and I go through the stages of these, it's going to make a hell of a lot more sense. So please stick with me. Thank you for watching, and aloha.